Hi everyone, today I'm going to introduce our work, Placement Initialization via Sequential Subspace Optimization with Sphere Constraints. This is joint work with Pengwen Shen, Chengquan Chang, my advisor, Albert Chern, Aoxi Li, and Yucheng Wang. Okay, so quick preliminaries. As you're probably all aware, modern techniques for doing global placement, they involve applying first-order methods like gradient descent to sort of nonlinear optimization problems. These are formulations of global placement that typically involve minimization of a wire length objective subject to some kind of density constraint. However, a gap in the previous work is that initialization of these methods is not sort of rigorously studied, and we were curious about the effect of initialization for sort of downstream placement quality. As we know, initialization plays an important role for the performance of neural network classifiers and more generally for the quality of solutions found by first-order methods applied to nonlinear optimization problems. So sort of motivated by this, we propose and investigate a couple different algorithms for doing initialization, in particular one that's based on a graph embedding formulation. So here's sort of our framework. We start by computing the eigenvectors of a graph model of the netlist. We then apply a Ridge transformation to align these eigenvectors with fixed vertices. These correspond to, in a layout, pre-placed macro pins or IO pads. We then apply an iterative method to find block global solutions to improve this initialization up here. And then we apply a global and detailed placement framework. Okay, so more concretely, here's one formulation of graph embedding as a spectral type problem. Here we have standard cell coordinates x and y, and we minimize a quadratic term with respect to a Laplacian L. So this is minimizing the squared distance between standard cells that have pins which belong to the same net. We also have a shift constraint, an origin constraint in orange here, and then something analogous to the density constraint mentioned previously in the context of global placement. So this is in red here, sort of constraint on the variance of our embedding. In previous work, we proposed an approximate scheme to solve that problem. You find the eigenvectors of L, and then you rotate them, you scale them to 1, satisfy the quadratic constraints, and 2, to align those standard cells that are connected to a macro pin or an IO pad. In this work, we describe an iterative method to improve this approximate initialization. The idea is it's based on sort of Newton steps adapted to our constrained optimization problem, and we extend this method further with a subspace scheme, just because, as you're probably familiar with, Newton's method is relatively expensive for quadratics. It necessitates inversion of RL, a Laplacian-like matrix, which can be done quickly, but iteratively the cost adds up. So in our paper, we exploit the fact that solutions to the aforementioned quadratic lie in a low-dimensional subspace. It's spanned by 8 things: the current iterate at time t, the Newton direction z, critically the small eigenvectors of L, and a gradient term as well. Importantly, you'll notice if we sort of discard this z and this v, this just basically corresponds to a gradient descent-like algorithm, minimization over a subspace spanned by the current iterate and the gradient. So the idea is we then generate a sequence of candidate solutions by iteratively solving the graph embedding problem within this subspace. It's very efficient because, L in this subspace just corresponds to something that's 8 by 8, an 8 by 8 matrix. And then we update the subspace. And additionally, we have sort of a reweighting scheme so that when we update subspaces, we're also reweighting L. And we do that because we show that, which again, you may also be familiar with, it's not new, that minimization of HPWL in the context of 2-pin nets can be formulated as solving a sequence of quadratic programs, reweighted quadratic programs. Okay, so our results are positive. We show significant improvements, up to 4% on canonical Adaptec Big Blue type benchmarks. This is in post-detailed placement wire length as opposed to post-global placement wire length, which improvements are of course to be expected. We also provide runtime details, so we note that while the cost of our method is not trivial, it's comparable to the cost of doing global placement. And in practice, a layout engineer would typically do global placement many, many times to basically do a grid search over various global placement parameters. However, when using our seed, since it's the algorithm is parameter free, one only needs to compute the initialization once. We also provide sort of a hypothesis test that's shown by these colored clusters. We say something like the standard cells that are close together with respect to the initialization, they stay together through global placement, so that provides more motivation for our method. Okay, so just some quick conclusions. Of course, initialization, proper initialization can help significantly improve the quality of placement engines that are based on first-order methods. SSM is very, very important to achieve sort of practical runtime on large benchmarks. And for future work, we're certainly more interested in integrating practical constraints, so things that are more intimately relevant for placement in the wild. So this includes stuff like timing reweighting. So I think DreamPlace 4.0 or 5.0 has done something similar, and we are particularly interested in sort of resolving this overclustering issue that is prevalent for spectral methods. And this necessitates sort of investigation of different notions of local congestion as opposed to the global orthogonality constraint or quadratic equality constraint we described earlier. Okay, thanks for listening. Appreciate your time. Let me know if you have any questions.